This video covers Chapter 7. It's an introduction to portfolio management. It is an important chapter. We're trying to kind of changing gears now in the textbook and the material that we're covering. And this chapter will help us, believe it or not, in security analysis, which is analyzing securities by themselves, which kind of sounds ironic because portfolio management is all about the interaction of securities. But as we'll find out in later chapters, understanding portfolio theory will help us with analyzing companies on a standalone basis. It's going to help us out with asset pricing models, which is the next chapter 8. Asset allocation, which is all about diversification. Equity strategies, as will come up in chapter 16, and evaluating portfolio performance. So it's an important chapter, and it sets the groundwork for really modern finance. So let's. The chapter is mainly about the work that Harry Markowitz did in 1952. He wrote a journal article basically on diversification. And so this model is often called the Markowitz model. Sometimes it's called the mean variance model, or just plain modern portfolio theory. It's called mean variance, as you'll see in a little bit. Normal distribution, which only needs a mean and only a variance to describe it, summarizes everything very nicely. Okay, so let's get started. Let's look at the assumptions of the model. The assumptions of the model is that investors have probability-based expectations for an investment return over a period of time, usually a year. So think of everything here. We're looking at returns and risk over a horizon of 1 year. And we have expectations around that. So an expected return, you could think of it as, what is my return in the future if I was to buy stock A, for example, being any stock? You need to have some idea about, is the economy going to be in an economic boom? Is it going to be normal economic times or a recession? And you got to have some probabilities around that to figure out, what type of return do you expect to get out of this stock, given those probabilities. So there's probability-based expectations. Investors also maximize expected utility. Everything translates. Given that finance is a subset of economics, everything we do should translate into economic concepts and economic theory. And in economic theory, we learn that money is really not, you don't get utility from money directly. It's the goods and services that you can convert money into that gives you utility and satisfaction. That's the way we're going to think about it in this chapter. There is a line of theory, though, it's somewhat new, that says, maybe some people actually get utility from money, holding money, cash itself. We're not going to assume that. We're going to assume that you prefer more returns to less, because more returns means that you have the ability to consume more goods and services in the future. We're also going to assume that people are risk averse, which is a really good assumption, and I'll elaborate what I mean by risk aversion in a second. We also, one of the other assumptions is that investors base decisions solely on expected return and risk. And so what that means is everything boils down to risk and return as the reason for your buying or selling a security and owning a security or holding a security in your portfolio. You boil everything down to risk and return. See, in this chapter, we have no risk-free asset, and it's an important point to make, to highlight that. The text doesn't do a good job. We're going chronologically here, where 1952, Markowitz comes up with this modern portfolio theory. Markowitz only dealt with risky portfolios, which implies there's no risk-free asset in the analysis. There were T-bills back then, but he did not consider it in his analysis. I don't think he gave it a thought at the time. He only focused on risky securities. And the other thing you also have to keep in mind with this chapter is that there was no concept in Markowitz's material on the market portfolio. I don't think it ever crossed his mind in that chapter in that journal article about what a market portfolio was and what it could do. It turns out to be an important concept that I'll address towards the end of this chapter and certainly in the next chapter. Okay, so now let's look at the preferences that individuals have. And this term preferences comes from microeconomics. What I'm about to talk to you about is discussed in the microeconomics course. And preferences, by what I mean by that, is risk preferences. There's three types of people that we're going to just look at briefly, and we're going to make an assumption here. So the first type of person is going to be the risk-averse person. Risk-averse. There's no D in there, by the way. Risk-averse person. And a risk-averse person demands a higher expected return for taking on more risk. Most people, when it comes to reasonably good-sized amounts of money, are risk-averse. You and I are basically risk-averse for the most part. For investments that have to do, say, with our retirement, material investments. We may actually not be risk-averse when it comes to, lottery tickets, for example. And I'll talk about risk-loving people in a second. But lottery tickets are small, $1, maybe $2 at the most. And so some people are willing to gamble in those terms, but not when it comes to big money. Most people are risk-averse. We're also going to talk about risk-neutral people. Risk-neutral people, all they care about is expected return. They don't care about risk. And 3, risk-loving people. Risk-loving people are willing to give up expected return to get risk. In other words, they're seeking a thrill that they get from taking on risk. We can model these people using indifference curves. And an indifference curve is nothing but a curve that shows you equal satisfaction all along the way. So you're indifferent wherever you are on that curve. Normally what we do is we write out what's called an expected return risk plane. It could be sigma here. And so this is the risk and return plane that we'll talk about through much of this chapter and the next, and it really shows you, what I'm going to show you is the trade-off between risk and return that people make. And so when people are risk adverse, they're going to have indifference curves that look something, at least have this shape. And let's try to put some numbers to it. Let's say this is 7%. So you got a 7% expected return. It's on this axis. And you may get, in terms of satisfaction, maybe we get 11 units of satisfaction. Sometimes it's called utils of satisfaction for a risk-adverse person. And so what it says here is when you have no risk, you're taking on no risk, and you get an expected return of 7%, you get 11 units of satisfaction. Now, if you take on more risk and you're out here, for example, you need a higher rate of return. Come up and over, you need a higher rate of return for that, but you still, in order to be indifferent between this point and any point, say here, in order for you to be indifferent, you need a higher expected return, which is what you're measuring off of this y-axis. And so if you take on enough risk and you start moving in this direction, you eventually come up to what's called a threshold that you don't really want to cross. And what it's saying here is, look, this slope is telling you how much extra return you demand for the given amount of change in risk. So it's the rise over the run. So the slope here, I'll write it down here, the slope equals your change in your expected return for a change in risk. And I'll measure risk as a standard deviation, which is what we do in this chapter. Markowitz only dealt with total risk, measures of standard deviation in this chapter. There's no beta in this chapter. It comes up in the next chapter. So again, this slope right here, so if you're at this point, this slope tells you the trade-off between risk and return. That's positive. Demand more expected return for a change in risk. Now, a risk-neutral person their indifference curve would look like this, and they would have to also be getting 11 units of satisfaction out of this because these two lines touch. The indifference curve is 11 all the way up along here, and since it touches at this point, It's got to be 11 all the way out here. And what you see is that a risk-neutral person doesn't care about it. Risk. You can take as much risk, they get the same satisfaction. What they care about is just looking at this 7% return, for example. A risk-loving person in difference curve would look something like this, an RL. And they also would get 11 units of satisfaction because, again, it's touching. All of them are touching, so they have the same level of satisfaction. But look at this risk-loving person. They're willing to give up expected return. They take on more risk because they're getting the thrill from the gamble. So in this course, we ignore these two types of people. Not a whole lot of risk-loving people out there, especially when it comes to big investing. They are risk-adverse to some degree. It's hard to tell and distinguish in some cases how risk-adverse people are. But I think what people sometimes mistake is that there are varying degrees of risk aversion. So you can have people who, for example, are not very risk adverse. Here's an example. Not very risk adverse. This person right here, draw it a little wiggly so you can better see it. This type of person's indifference curve means they have a much higher threshold for risk. Their threshold is way out here. They can take a whole lot of risk. And so they're less risk adverse than this person. You can have a highly risk adverse person who has very little threshold for risk. So you have varying degrees, and some people may interpret people like this. People who are not very risk adverse may interpret them to be risk loving when they're really not. They still demand higher expected return, but just not as much. And they have a much higher threshold for risk tolerance. Okay, now what we want to do is talk about ex post returns. And what I want to tell you a little bit of warning about the chapter textbook material. The textbook material spends a lot of time on ex ante. The textbook spends a lot of time on ex ante material related to portfolio theory. Ex ante means before the fact. It's where you have probabilities associated with expected returns and risk. It's almost useless from a practical point of view to use the ex ante math. The math gets kind of cumbersome, and we're going to have a fair amount of cumbersome math coming up. It's I don't think it's that bad, but at first you may think so. But we don't need to do the ex ante. It really clutters up a lot of the analysis in my mind, and we can look at ex post way better, far more efficient, and get the same intuition that we need, the important intuition around portfolio management using ex post. So we're going to get rid of this, ignore that. It's not going to show up in the test. It's not, and I'm going to steer away from it for any homework. I'm going to steer away from it in class. I'm going to look at ex post, and ex post means after the fact. Now, let's look at the expected return and the risk associated with portfolios of stocks. So this stands for the expected return of a portfolio. And what we're saying is the expected return of a portfolio is how much money, the weight that we have in stock A, times the expected return of A, plus the weight of B times the expected return of B. And so here we have a two-stock portfolio. The weights have to add up to 1. And it's simple. The return of your portfolio, if it has made up of stock A and B, it's got to be a combination, a weighted average of the two, and that's what's happening here. If it was 3 stocks, it would just be WC, expected return C, and so on. But the weights always have to add up to 1. So that's not, that's nothing special there. It's not complicated. It's pretty obvious. Markowitz would not have won a Nobel Prize for this, and people knew this already before he even did his analysis in '52. What he's really known for is the next equation, and that's the risk of a portfolio. And the risk of a portfolio, in other words, the standard deviation, the square of the standard deviation, which is really the variance of the portfolio, which measures how wiggly are the returns for a stock. Returns. So we're dealing with returns. See, R's, R's. No P's in here. The returns are functions of prices but we deal with returns. So you got more wiggly returns means more risk. We know that. And so you can always put a normal distribution on its side, and that's basically, here's the mean of the wiggly line I had, and here's the mean from a normal distribution perspective, right? And so all we have is, you have the mean here, and we have a measure of spread, how volatile the returns are. And so we got the mean, the expected, right here. And now we want the spread of this distribution, how wide this distribution is. It's going to be reflected in right here, in this formula. And that's why sometimes this is called mean variance analysis, because all you need is mean, and all you need is the variance to describe a normal distribution and to describe portfolio management, for the most part. So now, the risk of a portfolio is measured as the weight of A squared times the risk of A, the volatility of A, measured by the variance of A, plus the weight of B squared times the risk associated with B, plus 2 times the weight of A times the weight of B times the covariance of A and B. I'll just do it for a two-stock portfolio here. We could do a 3-stock portfolio. Let me see if I can get a different color here for you. We did a 3-stock portfolio. The math is basically the same, just as a couple of extensions here. Oops, that's C, sigma squared C. Plus we need a few more interaction terms. Here, a few more interaction terms, which I will derive this formula, and this is not a hard formula to derive. A little later on, towards the end of this video, I'll describe this for you. But what we have here is just looking at the 2-stock case. So let's get rid of this for the moment. Get rid of this. Get rid of this. Go back to this 2-stock case. Markowitz's insight, and the reason for his Nobel Prize, which came later, I believe in 1990 when he got it, was all about this term, the covariance between A and B. It's the interaction between stocks A and B. If you notice, when you look at expected return, there's no interaction terms here. It's just a weighted average of these things. Here, it's not a simple linear weighted average. I mean, you got squared terms here, and you got this covariance, this interaction term. It's the interaction term that we really want to focus in on. Now, there's 2 ways of dealing with this interactive term, this interaction term. The first way is, if you're given a correlation coefficient, right, it's the correlation of A, B, times the standard deviation A times the standard deviation of B. Now, covariance, you see, covariance, there's a V for variance here. Notice, the volatility is reflected in covariance. Volatility is not reflected in this guy right here. This is correlation. Remember, correlation goes from -1 to +1 in terms of a range. And so correlation does not have volatility wrapped in it. So you can just rearrange this formula and say, because covariance equals this, you can say that rho AB equals covariance AB divided by sigma A, sigma B. So the volatility washes out. It's on the top, it's on the bottom, and so you get this correlation coefficient. Correlation doesn't have volatility. And I highlight that because I know many people get confused between covariance and correlation. It sounds very similar. Okay, so now this is the easiest way to calculate covariance if you're given a correlation statistic. And also keep in mind now, let me get my red pen out, correlation, see this guy right here? Correlation can be negative, right here. This is the negative part, right? It can be negative. It's negative here, which means coming up to this equation, this whole term right here is positive because you got 2 squares. Multiply 2 squares together. This has to be positive. This guy has to be positive because these are squares. The 2 is positive. The W, if we assume no short selling, the W's are positive. The sign of this covariance term, which determines this sign is a function of what the covariance term is. If your correlation is positive and your covariance is positive, which means this sign is positive, which means risk of a portfolio is a function of this risk from stock A plus the risk of stock B plus the interaction terms here. If the correlation is negative and you're in this area, right, that means the covariance is negative because this is positive, There's square roots of something, so they have to be positive. This is negative, that means your covariance is negative, which means this sign is negative. So the risk of a portfolio then is this term, which is positive, plus this term, minus this whole interacting term. And if your stocks are perfectly negatively correlated here, what could happen is this plus this could be completely offset by this negative amount. And so your risk overall for your portfolio could be 0, which means your portfolio is not wiggling. Your portfolio return is constant, kind of like the risk-free asset, T-bill, which I don't really want to talk about too much because it's not part of this chapter. But in any case, if you have a sigma p that equals 0, you have a portfolio with no risk. Now, the benefits of diversification move in this direction. The lower the correlation, the higher the benefits of diversification. So you get maximum diversification here. You get no diversification. No diversification at correlation of 1. The real world, the correlation coefficients, depending on the sample, and if we look just at the United States, the correlation is between 0.40 to 0.60, right in this area. So there are benefits to diversification. They're not near as much as if you're out in this area, but there are benefits to diversification in the average stock. Now, if you go away from the average stock and you start investing in foreign stocks, for example, out of America stocks, you're going to start moving to the left. And you're going to get out of this range here, because this is just American stocks. You're going to start moving to the left, down towards 0. And if you start going into commodities or real estate, you're going to move to the left even further. And if you start going into, maybe Argentina real estate or real estate in Indonesia, you're going to have returns that are pretty much independent of each other, if not negative, and they're going to move in this direction. So you're going to get lots of benefits of diversification. And that's the point of this chapter. The point of this chapter is to learn about what drives diversification, this term right here mathematically, which is related to the correlations through this equation, and how to find and manage portfolios so that you manage the risk and you get the most you can from diversification, which means risk reduction. Okay, so diversification translates into risk reduction, and that's important. So even in a random walk market, even in an efficient market where you can't beat the market, all of this math and these concepts still hold. This stuff holds. And so you can believe in an efficient market and still use this analysis. Okay. Now, let me show you the second way of calculating this covariance term. There is another way. Kind of give you a little more intuition. As soon as I find my paper, a little more intuition. And the second way of calculating covariance is this. Covariance of A and B, which by the way sometimes is labeled, sometimes people symbolically say sigma AB, and when you say sigma AB with a little comma there, it means covariance. Just another way of writing it. And the way to write this is as follows. It's going to be, I'm going to use two stocks, I'm going to look at 2 stocks over 3 periods, and I'll graph it out for you in a minute, but I want to throw the equation at you first. So So I'm going to look at return of stock A in period 1 minus its expected return in period 1. And I'm going to multiply it by how return of B in period 1 behaves relative to its mean. And I add to that how the return of A relative to its mean behaves in period 2, multiplied by how B behaves relative to its mean in period 2. The same thing with period 3. Now I'm going to take these three components. See, that's a number. These are two numbers multiplied together. So there's four numbers here. This is a return. This is an expected return. This is a return. This is an expected return. In brackets here, this turns out to be one number multiplied by another number. It turns out that this whole thing is one number. The second row is another number, and this third row is another number. We want to add those up. So I should put the bracket right here at the end. And divide by n minus 1. Now, keep in mind that your chapter textbook kind of changes between how it averages things out, and that's what you're doing. You're averaging things out, assuming a sample here. Remember from probability, when you subtract 1, it's a degree of freedom adjustment. I don't care if you divide it by n or n minus 1, so long as you're averaging. Remember, when you assume a population, you divide by n, but when you have a sample, n minus 1 shrinks the denominator a bit and boosts this number up to account for a sample. You may not get all the volatility that you think you would compared to a population. Again, that's statistical trivia. Leave that to the statisticians. We just want to apply it and get the concepts in this class. Okay, so that's what covariance does. Now, how does this mess, you might call it a mess, it's really not. It's very intuitive. The math here is very intuitive, and I'll show you graphically. So the best way to do it is I'm going to assume stock returns that have a correlation of -1. Correlation row, -1. So a row is nothing but an italicized P. And so here are the returns, for example, of stock A. Returns of A. They're quite wiggly, right? So here you got an economic boom, not so good of times, boom, not so good of times, and so on. And then you can have the return of B. And the return of B is going to be just the opposite of what A is. And so when A is doing well, B is doing poorly, and vice versa. So what you have is you have two stocks that are, their interaction terms are basically offsetting each other, because a couple of things. One, the expected return of A and the expected return of B, the way I drew it, and it's contrived the way I drew it, but oops, I should put it expected. The means of these are both equal because they have to take the return right down the middle. Means go right down the middle, right? Which is basically another way of saying, look, you take a normal distribution, if it's normally distributed, the mean's right down the middle. Okay, so now what happens is you got the means right down the middle. If you form a portfolio, let's say you put an equal weight into each stock, right? Then this is going to be offset by this, because this is a negative deviation from the mean. This is a positive deviation from the mean. The two are going to offset each other, so you're going to have a portfolio that looks like this. So the return, expected return on your portfolio, right? This could be, maybe this is 8% here. Right? You put a 0 down here if you want, but this is 8%. That means you got an 8% return that's risk-free because it's a straight line. It's not wiggling from its mean. There's no uncertainty here. And so we can match these concepts up to this math. So here we got the return of A in period 1 minus the average of A, basically. So if we look at this, assume this is period 1, period 2, period 1, period 2, period 3, then this deviation is positive, this deviation is negative. So the A, which is the thick, heavy black line right here, This is a positive deviation, so this term is positive. Now B, how does B behave at the exact same time? Well, it's negative, so this deviation is negative. So a positive times a negative means this whole term right here, top term, is going to be negative. In period 2, the deviation of A is negative, so this is negative, and this is positive right here. Deviations of B are positive. That means this is positive. So a negative times a positive is negative. Okay. And for period 3, the A deviations are positive here. They're negative for period 3 with respect to B. And so this term is negative, this term is negative, and this term is negative. And then you're going to average them all out. You're going to get a negative covariance term because they're negatively correlated, which translates into a negative sign here like I have. And so the risk of a portfolio is going to be this plus this minus this whole term. Now, if we pick the right weights, and that's what a portfolio manager has control of, and the only thing the portfolio manager has control of, pick the right weights, say 50-50 between stock A and B, then you can actually get the risk of the portfolio to be 0 because it'll perfectly offset. There is no wiggling in the portfolio return. It's a straight line. So therefore, I can translate this math, this formula, which looks kind of bad, into something that's relatively intuitive under the assumption of perfectly negatively correlated stocks. You should get the maximum benefits of diversification there, which is risk reduction. Okay. Now, we can also look at a row of positive 1. And so let me show you a row of positive 1. A row of positive 1 will look something like this. You got the return of A, and then you got the return of B on top of it. Return of B on top of it. They're perfectly positively correlated, but when one's above the mean, the other's above the mean, because here's the mean basically. Here's the expected returns of both A equal expected return of B, the way I've contrived this. But when they're both above the mean, they're here, right? Here they're both below the mean, here they're both above. So if this is period 1, 2, and 3, like we had before, then the math here is saying, well, the math in this formula is saying that when the return is above the mean, this is positive. This one's also above the mean at the same point in time, period 1. So positive times a positive means this whole top term is positive. Now, when they're both below the mean right here, period 2, then this is going to be negative, and this term is going to be negative, and negative times a negative means this whole term is positive. And in period 3, they're both positive, so this is positive, which means this term is positive, and the average is going to be positive, which means this covariance term will be positive, which means going back to this formula, this is going to be a positive number here, because this covariance is positive. And so the risk of the portfolio is equal to this component, plus this component, plus this interactive component, and this will not equal 0. And you can see that graphically, because if you form a portfolio where 50-50 is in A and B, you're going to have a portfolio that's just as wiggly. So the return in your portfolio is going to be here, RP. The return of your portfolio is going to wiggle just as much. The expected return, the average part, will be right down the middle with the other stocks, but the portfolio will be just as risky as the individual stocks. You'll get no benefits of diversification from buying two stocks that are perfectly positively correlated. And you can think of it as being Coke and Pepsi, two automakers, computer chip makers, for example, where they're subject to the same types of risks in their marketplace, in their competitive environment. Causes the stocks to move in sync with each other. Okay. Now, let's do an example, a mathematical example of this. And I'm going to show you an example. It's a little different than the problem in page 5 of my notes. I'm going to show you how to make up a problem. I want to make up some problems that are slightly different than the notes so that the material you get from my lecture will be slightly different in terms of examples than what you get here, so you get 2 different examples or more so this way. Okay, so here's the problem I'm going to throw at you. We have 2 stocks, A and B. So we got expected, we're just going to call this returns, and I'm going to call this risk for 2 stocks, A and B. You got period 1, 2, and 3. And so it's a 10% return in period 1 for stock A, minus 17.5 here, and a 15% return in period 3. So you add this up and average them. The average for this is 2.5%. Which kind of makes sense. You can eyeball it. 10 minus 17 plus 15, average it, divide by 3, and you get 2.5%. The rest, this is stock A. This I'm going to label the returns of B. So I'll label this return B. The return of B will be minus 8, 17, and minus 5. Average it out, it's 1.33%. I'm going to put the weights. I'm going to put half my money in A and half my money in B. I'm just giving you this by assumption. All this material is given, and from the given I can calculate the averages, but so far everything else is given to you. And then from this we can calculate the variance and the standard deviation, which you ought to be able to do, because we're just taking deviations to the mean. So we're taking this number, subtracting the mean, squaring it, and adding this number minus the mean and squaring it, and adding this number minus the mean and squaring it, and averaging them out. And so we would get a variance of 306.25, a standard deviation of 17.5, 186.33, and 13.65. I can show you that real quickly because I'm sure you're going to have a math question, but I'll calculate this one for fun. I'm going to, here's how I'm going to do it. I'm going to take this 10% return, subtract the mean, and square it. And I'm going to take this deviation from the mean, minus 17. How does that deviate from the mean? Square it. And I'm going to take 15, subtract the mean, square it. Add them all up, and I'm going to divide by n minus 1. N is 3. 3 minus 1 for a degree of freedom adjustment. Remember, it's slightly different than what you got in Chapter 1 where we divided by n. And when we do this, we get 306.25. Take the square root of this, and you get the 17.5%. Now, keep in mind that when you have variance, it's percent, and that's, again, you'll never see that in a textbook or anywhere else except by me, but what that does is it warns you that this is variance, and variance is in returns squared, which are not easily interpretable. It's a little hard to interpret that. Once you take the square root, you get back into original units, and you get 17.5%. So when you deal with a normal distribution and you graph it, and you get returns here on this axis, so you got an expected return of 2.5%, and the standard deviation is 17.5%. The standard 17.5% is telling you just the spread here. This is in percent, the spread is in percent, so it's consistent. Okay, now, so I'm still laying out the information for you. Now, if you calculate, we should, before we go further, calculate the covariance between these securities. The covariance between A and B. Okay? And we can calculate that. We're going to calculate it according to the formula I showed you. This formula. Okay? Because notice, I did not give you a correlation coefficient. You can't use this formula right here, the rho A, B, sigma A, sigma B for the covariance of AB. Can't use it. I didn't give you a correlation coefficient, so you have to go back to this formula. So now, let's calculate it. I'm going to take the 10% minus its mean for A and multiply it by how B behaves in this first period relative to its mean. Okay. So this is positive, this is negative. Oops, sorry about that. This is positive, and this is negative. So this is 10 minus the mean, period 1 here, and minus 8 minus the 1.3 here, which is negative. So this whole term is going to be negative. And you can spot this with your eye. You don't need to do any math to figure this guy out. This has to have negative covariance. Because when this is above its mean, this is below its mean. When this is below its mean, this is above. This is above, this is below. You know that these two securities are one's up, one's down constantly. And there has to be negative covariance. There has to be offset. So before you do any math, you know this number is going to be negative. And so far it looks negative. Let's do the next one again. Next one, we're going to take this minus the mean, and then 17, multiply it by 17 minus the mean. So minus 17.5 minus 2.5, multiply it by 17 minus 1.33. And this is negative, this is positive, which means this whole term here, this is negative, this is positive, this whole term is negative again. So add the next term. 15 minus 2.5 minus 5 minus 1.3. 15 minus 2.5, that's positive. But minus 5 minus 1.33, that's negative. So positive and negative is negative. Add it all up, divide it by 3 minus 1, and this whole thing equals negative 231.25. That's the covariance. Negative 231.5. Notice covariance doesn't really have any bounds to it because it has the volatility measure in it, like you see up here. Correlation is bounded between negative 1 and 1 because these volatility estimates here, sigmas, are unbounded. Your covariance can be any number. And so looking at negative 231, to me, it doesn't mean anything to me because I can't put a boundary around it, so it's hard to interpret. Now, we can calculate the correlation to get an interpretation of how these offset. So the correlation here, solve for, since we know the covariance, and we know this term, and we know this term, we can solve for rho. So rho, again, rho sigma A, sigma B equals the covariance of A, B. Well, this equals 231 minus 231, 25.25. This is 17.5 right here. 17.5 is the standard deviation. The standard deviation here is 13.65. And so we have rho A, B, solve this one equation right here for rho. And so rho A, B equals minus 0.97 round. Almost perfect positive negative correlation, which means we're going to have a lot of benefits of diversification. So we form a portfolio between these securities before you do any math. You're going to see that the standard deviation of the portfolio is going to be substantially less than these two wiggly portfolio, individual stocks, A and B, measured by the standard deviations. Let's see. Let's do the math. So we're going to use this formula. We have all the numbers. I gave you the weights of 0.5, so 0.5 squared for A. This is 17.5 squared. The weight of B is 0.5, and this is 13.65 squared, 13.65 squared, plus 2 times 0.5 times 0.5 times minus 231.25. This negative sign means that this is negative. So we can get rid of this negative sign here. Just put it out here. So look, the volatility of your portfolio formed between stocks A and B is going to be this plus this minus this whole term. And so what it amounts to be is this. First term here is 76.56. This term is 46. Trouble reading my writing. I think it's 5.8. And then minus this term is 115.625. All said and done, this is 7.52%. Sorry about that, because we're calculating the variance. That's how volatile the portfolio is. Let's take the square root of this, and we get a sigma p equal to 2.74%. There it is. There's the risk of the portfolio. Now, how does that stack up? Let's take a look. The risk of A was 17. The risk of B was 13.65. We formed a portfolio between the two, and since they offset each other greatly, the risk is substantially lower at 2.74%. Now, let's draw it out graphically so you can see it a little better. Get another piece of paper. Okay, and we're going to draw a graph. So here's the risk and return plane. And we're going to put in stock, let's see, stock B, 17.5 standard deviation with a 2.5% expected return. Okay, this is B. And A has a standard, oh, wait a second, mixed up here. This is A. Sorry, this is A. B is right here with a 13.65. Oops. Let me fix this. I draw it a little too far away. Wait it out. B is going to be 13.65 with a 1.33 average that was given. So you got A and B as given, and then we formed a portfolio where the risk was 2.74% standard deviation with an expected return, which we didn't calculate, I don't think, but we can do that pretty quickly. Remember, here's our returns. We had a portfolio 50-50 in this weight with this average and this average. So it's 0.5 times 2.5 plus 0.5 times 1.33. And so the average comes out to be we can find it. I just might as well get my calculator out. I can't find it. 0.5 times 2.5 plus 0.5 times 1.33. And this is 1.915%. About 1.9% is the portfolio's expected return, 50% in each. So this is 1.91%, and here is the portfolio P. Now notice what happened. Get it in red here. If you put 100% of your weight, if you were to do that in stock A, you'd be right at this point. You'd have a standard deviation of 17.5% and expected return of 2.5%. If you put all your money in B, you'd have a 13% standard deviation, 1.33% expected return. If you form a portfolio, since these securities interact negatively with each other, you can actually get a return, a risk that's outside of this range. Here's the range of risk, and I just went whoo, all the way over here in terms of risk. But notice the return is right down the middle of these two, because I put 50% in this, 50% in here, and I got 1.91. And so there's the portfolio return. So what happens is, given this level of risk, or given the correlation coefficient, I basically have a portfolio that could look like this. So I draw these together. And so what I'm saying there is this. Start from the beginning here. If I put 100% of my money in A, 100% in B, if I had perfect positive correlation, there'd be no benefits of diversification. And as I change my weights between the two stocks, I would be somewhere on this line with perfect positive 1 correlation. If I had correlation slightly less than 1, and I drew a portfolio where I changed the weights that I have invested in A and B, I would start to move out to the left. This might be a correlation row of AB, maybe 0.80. And if I had a correlation of maybe 0, if I had correlation of 0 and I changed the weights, which is all I can do, change the weights, so I change all of the math that I had here, because here's all the math where the weights are, right? Change all of those W's. Then if I had this was a correlation of 0 for A, B, I could get somewhere along this line, depending on where I pick my weights. And when I have correlation row of negative 0.97, here I am, right at this point, and all I have to do is, if I change the weights, I put 100% of my money in A, I'd be right here. Now if I put 99% of my money in B, 99% of my money in B and 1% in A, I'd be right here. And I put 98% of my money in B and 1% in A, I'd be here. And I keep changing those weights, I could get these points. I could draw out this, connect the dots, and be all the way over to a point here where I got 99% of my money in A and 1% in B. I'd be right there. And so on. Now, if I had perfect negative correlation and I picked the right weights, I could actually, get green pen here, I could actually get to the point where I could be on this axis with no risk if I had perfect negative correlation and the right weights, which means I effectively, if I had perfect negative correlation with no weights, they'd perfectly offset each other. I'd have a portfolio with absolutely no risk, no volatility. No risk and no volatility on this means I'm on this axis, right at this point somewhere, right here where I got the green. You can't really see in green, but that'd be somewhere about here. Okay, so what I'm saying is, let me draw you a cleaner graph. When you have different two portfolios, two stocks, X and Y, if they're perfectly positively correlated and you change the weights, you're going to get a portfolio somewhere on this line with perfect positive correlation. If there's slightly less than perfect positive correlation and you change the weights, you're going to get this bowed out shape. And you're going to have the ability to get out of the range in terms of risk. See how I'm getting out of the range with risk here? I have the ability, if I pick the right weights, I can get into this area. But I'm still keeping the expected return range here. Now, as the correlation goes lower, assuming lower correlation, I can get more benefits to diversification, to the point where I get perfect negative correlation. I can actually touch this axis and have no risk, zero risk right there with a return. So you'll see this graph in your textbook, and each line represents a different correlation coefficient, and each dot represents a different portfolio that's composed by picking different weights. Okay. Now, let's look at the efficient frontier. And that's the subject of the next page, is the efficient frontier. So let's look at the efficient frontier. I'm on page 6 of the notes. So, efficient frontier looks like something like this. Let me draw it, and then I'll define it for you. Expected return and risk plane. The efficient frontier looks something like this. That looks kind of similar to what we just saw earlier, a few minutes ago, except these are dotted, dashed lines. I'll explain that in a second. So I'll call this the EF, efficient frontier. And so the way this is composed is you got a bunch of portfolios of security. You got individual securities of stocks out there that have a high sigma. Individually, they have high sigmas, right? But when you form portfolios of all of these and you invest in all of these securities, you can get this efficient frontier, just like I showed you a minute ago, with our two-stock portfolio here. Okay, so I'm really showing you something that looks like this, except with the whole market. And so if you were to form portfolios between these two securities here, you might get something that looks like this, and between these two securities, something that looks like this. And when you start forming portfolios of 3 securities, you get even more diversification, so you go out to the left even further, to the point where you add all the securities in there, you get this bowed out shape of the efficient frontier. And you get on these different points, see, these are all different points based on the different weights that you have invested in all these stocks. Different weights. Okay? And it's given, this shape is given by the fact that the average correlation is between 0.4 and 0.6. So this is the type of correlation. You won't get something in the real world that bends out and touches and moves out like I showed you earlier. It doesn't do this because in the real world, correlations aren't -1. They're not 0. They're 0.4 to 0.6. You got many stocks, so you get some benefits of diversification just adding stocks. So now, the definition of the efficient frontier is this. It says, for example, for a given level of return, so just pick a level of return, just given level of return, the minimum amount of risk portfolio. So you come over to here, what's the least amount of risk that you can get given this return? Let's say it's 12%. Well, anything in here is inefficient. You can get in here, form inefficient portfolios, suboptimal portfolios. You'd be in here, but you really wouldn't be doing very well because you're not getting much utility out of being here. You get more utility going in this direction, where you get low risk here in this direction, low risk, and high expected return. So risk-adjusted returns say you want to be up in here, but it's unattainable. The best you can do is you can be on this frontier, and you're inefficient inside the frontier, and to the left of this frontier in the upper part, this is unattainable. You can't get there. So the definition of an efficient frontier is given an expected return, what's the minimum amount of risk? It's got to be right here. It's the minimum amount of risk you can get. Or the other way to look at it is, given a level of risk, what's the maximum return you can get? So here's a given level of risk. Maybe it's a standard deviation of 18%. You come up, here is the maximum amount of return you can get for a given level of risk. That's defined to be an efficient frontier. 2 different ways or angles you can look at defining it. Given a return, minimum risk, given a risk, maximum return. Now this is not an efficient component right here. You would get this if you form portfolios between these stocks and if you change the weights. But these are not this is not an efficient area, because if you pick a certain risk, this is not the maximum return you can get. The maximum return would be up here, right here instead. So these are inefficient areas of the efficient frontier. Now, let's develop this a little bit better, and it's important. This efficient frontier seems a bit abstract, but I can tell you that nearly any version, nearly any edition of that's the Financial Analyst Journal and it's the February 2015 edition here. Nearly any time this journal is published, they have a graph of the efficient frontier. And this is a very practitioner-oriented journal, and here you got it, the efficient frontier. Right? And they're drawing it and they're describing it. They have other pictures of it. And so this is the foundation for the article talking about it. And so here you got expected return. And here's the funny thing is they say variance of returns. What they really mean is the standard deviation of returns are here. Or in other words, the volatility of returns. There's a little typo in the graph itself. But they're talking about this in the article. Now, let's go a little further and develop this. Let's look at optimal portfolios for an individual investor. So we have risk, expected return. So here you have the entire market of individual stocks, risk and return. Form portfolios, given the whole market. Here you are, you have an efficient frontier of all the stocks in the universe. This is sometimes called the universe of all the stocks out there. Thousands of them. Form portfolios, this is the best you can get. This is unattainable here. This is attainable but inefficient. And you want to go in this direction. You want to move in this direction as best as possible. So you're going to be on this frontier. Can't get past it. But you really love to be out here. Now, people have indifference curves. Individuals have indifference curves that could look like this. So here you get somebody with a certain amount of satisfaction. Maybe they get 10 units of satisfaction here, where they're risk adverse because it's upward sloping indifference curve. And the slope here is measuring the change in return for a change in risk. Okay. And right at this point, we have a tangency point. The two lines are tangent. When you have two lines that are tangent, they have the same slope at this point. See if I can get it in there as best I can. Basically, they have the same slope. That slope measures the change in expected return for your portfolio or stock divided by the change in risk. That's basically your risk-adjusted returns. Remember risk-adjusted returns, except you minus the risk-free rate. Remember we did that? But here, this chapter, remember, we don't have a risk-free rate, so ignore the risk-free rate. We're looking at the change in your expected return for a given change of risk. So this slope is what you want, and you want to try to maximize this slope, because the steeper the slope you get, the better, more return you get for the level of risk. So you take a little bit of risk, you get a high expected return with a steep slope. Okay, so this is for an individual's utility function, where they get utility as measured by indifference curves. Now, the slopes are the same, so really the way you can interpret this is, look, here's what the market is offering in terms of risk and return. Right? This is what the market's looking for. This is what the market is supplying. Individuals are demanding, this individual is demanding utility, this much utility. And by the way, the individual would have utility lines that look like this. This person would get maybe 12 units of satisfaction here, 14 units of satisfaction, but look, this person can't get 14 units of satisfaction, can't get 12 units of satisfaction. The best they can do is get 10 units of satisfaction here. They don't want to get 8 because that's suboptimal. 8 would mean suboptimal level of satisfaction. So you want a tangency point. So what I'm saying is, this is the supply that the market's offering in the efficient frontier, given the risk and return. It's matching up with the demand that an investor has, which is measured by their indifference curve. So supply equals demand is a tangency point. We basically have an equilibrium between this investor and what the market is supplying. This individual wants an expected return of this amount, whatever this might be, maybe it's 15%, and wants this level of risk. Okay, now let's go one step further here. Let's go and look at the entire market portfolio. So here you have the efficient frontier for all stocks in the world, the universe of stocks, and let's aggregate everybody's indifference curves. In other words, let's look at the indifference curve for all people, all investors, aggregate them together. Just like, remember in macroeconomics, you aggregated consumers, you aggregated government expenditures, you aggregated imports and exports, all aggregated together. So we're going to put together an aggregate indifference curve. Call it IC. The indifference curve where everybody's smashed together. Look, you have a tangency point, and what's offered by the market in terms of supply is going to equal what the average investor is looking for in terms of demand, what they demand from the market in terms of risk and return trade-off that they demand versus what the market's offering. It's equal right at this point where there's a tangency point. There's an equilibrium there, and that equilibrium is really important. Markowitz did not realize this in 1952. But he grappled with the concept. It wasn't until Sharpe in the early to mid 60s figured it out that this point is M. M stands for the market portfolio. Again, which is not really discussed in your textbook in this chapter, but what I'm trying to do is lay the groundwork for the next chapter. Tell you what Markowitz missed, because what Markowitz missed is what people picked up later on. So in 52, Markowitz comes out with this modern portfolio theory, which I just explained. A guy named James Tobin in 1958 figures out that, look, Markowitz forgot the T-bill, forgot the risk-free rate. Markowitz throws it into the mix and develops it. Tobin wins a Nobel Prize in 1990 along with Markowitz for that and other work. And then Sharpe comes along in the early 60s, adds the market portfolio, comes up with the capital asset pricing model in the mid-60s, which is the subject of the next chapter. So I'm trying to, right now, bridging between the two chapters and, kind of going from the late 50s to the early 60s at this point. So there's the market portfolio. Take a look at your book. Take a look at nearly any investment textbook. You're going to see this graph, and you're going to see a little thing called M there. Okay. Now, let me derive this formula for you. I told you I would. So I'm going to derive it for a 3-stock case. And where the heck did I get this from? Where did Markowitz get this from? I'll do the shortcut notation instead of writing covariance out. Sigma AB. So I'm taking into consideration all of the interaction terms between stocks A and B, the interaction between A and C, and the interaction between B and C for a 3-stock portfolio. So where does this ugly equation come from? Well, it comes from a variance covariance matrix. So let me see if I can do it here. Okay, so what I'm going to do is I'm going to put the return of A minus the average return of A. Instead of calling it expected with the E, I'm just going to put a bar meaning the mean, so I have enough space here. And I'm going to say the return of B minus its average, and the return of C minus its average. And I'm going to do the same thing along this axis, RA minus R bar A, RB minus RB, RC minus RC bar. Okay, there I have it. Now, what I'm going to do is, let's look at when we multiply this term by this term, what do we get? Well, we get the variance of A, because remember the variance of A is nothing but take RA minus R bar A, square it, and divide by n, or n minus 1. So we can think of this whole thing, taking all the terms in this matrix and dividing it by n, and I think n minus 1 we'll use in this chapter. So we'll divide everything by n minus 1. But the point is, this term is RA minus A RA bar times RA minus RA bar. This deviation times, this deviation right here is the squared term. I'm taking this, multiplying it by this, and I'm getting this A term. If I do the same thing for the B's, I get sigma squared B, and for the C's, I get sigma squared C. Okay? Now, don't forget we have weights here. I have left out the weights in this math, but I have a whole pile of W's in this equation. So you can think of WA here, WB here, WC, WA, WB, WC. And so when you take WA times WA, you get WA squared. WB times WB is WB squared. WC times WC is WC squared. Now, I just showed you this diagonal equals this term plus this term plus this term. And that's the diagonal, the variance-covariance matrix. Now, the off diagonals, for example, how does A behave relative to B? Multiply this by this, right? And wow, what do you get? You get the covariance between A and B, which is this term right here. So, and you get a WA in front of it and a WB right here, which is this term, and this term. Now, where do you get the 2 from? Well, the 2 comes from the fact that WB, WA, sigma BA is the same thing. These 2 equal, so you have 2 of them. So the 2 comes about by the fact that you get 2 identical off-diagonal components to this matrix here. And you're going to get 2 identical off-diagonal matrices here, components here, is AC versus CA. These 2, this component, this is going to be equal, so you're going to get 2 of them. So you're going to get the weights of A, the weights of C times AC. You're going to get 2 of them. And the same thing here, you're going to get these 2 are going to be equal. And that accounts for this 2 in this covariance term. So what happens is you get, this is an n by n matrix where n is 3. N by n matrix. But notice, look, we have how many components? We have 3 stocks, we have 3 variances, 3 variance components, 1, 2, 3. How many off-diagonal, unique off-diagonal components do we have? Well, not even unique, but how many off-diagonal components we have? We have 1, 2, 3, 4, 5, 6. So we have, to summarize, we have n variance terms, which equals n is the number of securities, and we're going to have n times n minus 1 covariance terms, because we're going to have a total of n times n terms, because this is an n by n matrix. And so the variance is n, and we're going to subtract out that this minus 1 accounts for these variances. And so the number of covariance terms is going to be n times n minus 1. So it's 3 times 3 minus 1. That equals 6. That's how many covariance terms. 1, 2, 3, 4, 5, 6. Got it? To me, this is a bit insightful. It's how it's derived. This is when you can program portfolios in a computer. You throw things into a variance-covariance matrix and even a correlation matrix, because each one of these components has a correlation behind it. And the correlation of something with itself is 1, so it's 1, 1, 1, and then you got the correlations of the interaction, which will be different than 1 in most cases. So that's where a variance-covariance matrix comes into play. Now, one more thing before we leave this chapter. It's a little conceptual, but I think it's important because, again, it's going to lead into the next chapter. And that is the idea of a paradox situation. And I'm on page 9. Page 9 of my notes. It's a paradox situation. It basically says this. I'm trying to find my The paradox situation is this. Basically, graphically, the paradox situation says, look, you got these two wiggly stocks, two volatile stocks. They each have a fair amount of risk. That's why they're wiggling around. But when you form a portfolio between these two stocks, it's riskless. That's why it's a straight line right here. Now the question becomes, how can you have individually risky stocks with a high mean, a high expected return, let's say 13%, but a portfolio that earns 13% and it has no risk? You know, if you think about it, there should be some smoke coming out of your head at this point, because it doesn't make sense. Something's missing from the analysis. Something is incomplete with the Markowitz analysis. In other words, the Markowitz analysis makes a whole lot of sense. It's extremely useful. It shows up everywhere, even right present journal articles on it. But it's a stepping stone. It leads us to more sophisticated models that make a little more sense. But what we see here is we see what's called the Markowitz paradox. Two risky securities that form a portfolio that's risk-free with a very high expected return. Doesn't make sense. That should have a much lower return. And what it leads to is to you know, okay, so it tells us that there's signals that there's a problem with Markowitz's theory by itself, and something else is important to the world of portfolio management. And what is that something else? That's what I'm going to show you. So the way I'm going to do it is I'm going to look at I'm going to take the risk of a portfolio, and I'm going to have N stocks in my portfolio. I'm going to look at the risk of an N stock portfolio, N, whatever N is, and I'm going to calculate the risks where I have an equal investment in each stock. So here I got stock 1, and here's the variance of stock 1. And how much, if I have an equal weight in N securities, so if N was 2, I'd have 1/2, the weight would be 1/2, and it would be squared. And then I'd have stock 2, where I have a weight of 1 over N times the sigma squared of stock 2, and so on. And I keep adding that, add that up. Now, that's the main diagonal, the variance-covariance matrix. Now let's capture the diagonals, the interaction terms. So it's going to be 2 times the weights. Here's the weight of the one, here's the weight of the other, times the covariance of 1 and 2. And it's 2 times 1 over N, so I got the weights. Since everything's an equal weight, and there I got my covariance terms. I got 6 of them, 6 off diagonals at this point. Okay. Now let's assume that we have an average variance for stock I. That's an I right there. Can you see it? It's a little I. Draw it a little better. There's an I, stock I, and that's the variance. I'm saying it's an average. Let's assume every stock has the same variance. We'll put a little bar over it. And that all the covariance terms, since they all have the same variance, they must have the same covariance term. I'm going to make that assumption. Almost can say that. So I'm just going to make the assumption that the covariance between stocks I and J all have the same covariance, the average covariance term. So I'm just going to make that assumption so I can collapse this math down a bit. So what happens is when I have an average variance and an average covariance for each stock, what I can do is I am going to have 1, 2, 3, I'm going to have N. I'm going to have N components of the variance. Right? Just the number of components that I have on the main diagonal is going to be N. So it's going to be N times the weight of each, sigma I squared. So what I just did was I took all of this, get it in red here, so all these terms, dot, 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 all the way out to infinity, I collapsed all of that into this component right here. Okay, so I just took this part up here, collapsed it down to this little equation, And now I gotta get all the covariance terms here. Well, that won't be too hard because we know there's n times n minus 1 covariance terms. Remember I calculated 6, and here's 6 for 3, but this really goes on dot 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 here because there's, if we have n, you're going to have a whole bunch of, you're going to have n times n minus 1 covariance terms all the way down. So I'm going to take that, I'm going to multiply it by the weights. Don't forget those weights. Remember, like we saw, back here, 2 times the weights times the weights times the covariance terms. There's the weights. Okay, times the average covariance between stock I and J. Okay, and now, so I boiled all of this down to this component right here. And what I want to do is I'm going to say let n go to infinity. Right? Oh, nah. Let me back up 1 second. Let's consolidate now the math here. So n over 1 over n squared is going to be equal to 1 over n times sigma I squared. Okay? So I just simplified this. I'm going to simplify this down because n over n crosses, the n cancels out, and it's n minus 1 over n. N minus 1 over n times the average covariance term. Now what I'm going to do is I'm going to let n go to infinity. Well, I'm going to assume there's an infinite number of stocks here. And what happens when I let n go to infinity? This term right here goes to 0. 0 times the average variance means that all the diagonal goes completely, disappears. All these terms disappear, which means none of this counts. Cross it right out. And when you let n go to infinity, this term right here becomes 1. It's basically, if you got 999 or 1,000 securities, n is 1,000, you got 999 over 1,000. But as n goes to infinity, this is basically 1. So this washes away, it's basically 1, and all you're left with is the average covariance. The point is that when you have a large portfolio, the risks of the individual stocks do not count, they wash out. All that matters is the average covariance term. And what is the average covariance term? Well, the average covariance term is represented by the market, the average stock in the market, which is that little point M that I showed you with the efficient frontier. This. That point M. So what the next chapter is all about is describing point M and how the market portfolio is what we want to capture. So that's what Markowitz is missing. Markowitz is missing this math in the analysis because what it does is it signals that average covariance counts. And the average covariance counts, it's coming from the market portfolio. Somebody has to hold the market. If it's outstanding, somebody has to invest in it. And it's the average covariance. And so what is the market portfolio? Well, it's basically a value-weighted index that we had looked at earlier. It's not a price-weighted index, it's value-weighted because a value-weighted index is the only index that you can have for the market overall. If there's a market cap that's outstanding for stocks, there has to be somebody holding that market cap. Portfolio M.